Okay, let's get started. Hello, everyone. Thank you very much for coming. My name is Yue Sun. I'm a PhD student at the University of Tokyo. Today, I'm going to present our work on feature distribution matching for federated domain generalization. So this is a joint work with Enjun and Hideo LGI. So I'm going to start with one of the limitations of current machine learning, which has to do with the generalization outside of the training distribution. We use data from one distribution, some of it is used for training, and then we apply the training model to other data from the same distributions, like the test data set. However, the real world is not like this. A significant concern is that the deep neural networks usually struggle in the out-of-distribution settings, though they have shown good in-distribution performance. One of the problems for the out-of-distribution is the domain shift problem. It refers to the distributional shift between the train and test data set, which will hinder the trained model's performance in the test set. Let's consider a trained data set DS and a test data set DT that share the same support of the input and the output space X and Y. And their inputs have a domain discrepancy showing specific styles due to factors like the data collection environment. For instance, to tackle the digital image classification task, as shown on the left-hand side, some domain data has a more complex background with more irrelevant information. So the main challenge here is how to use the reusable knowledge in the trained dataset to tackle the new task in the test dataset. Such transfer learning task, what we want to do is to learn the conditional probability distribution for the test data using the information from the trained dataset DS here. First, the transfer learning is a machine learning method where we use a pre-trained model as a training point for model or new task. On the other hand, we can distill the reusable domain irrelevant knowledge representations and discard other irrelevant information for the trained model on the source domain, so that the trusted representations then will allow us to learn the target domain task more efficiently. On the other hand, we can also reuse the parts of a previously trained model or a new network tasked for a different but usually similar problem, so that the new network can be trained more efficiently with fewer samples. So in this work, we consider the transfer learning problem in specific settings, which is federated learning. A federated learning framework usually consists of a global model with on the parameter server, and we have multiple local client models. A client in the federated learning usually cannot share their training data, mainly due to the confidentiality and privacy issues. Instead, the federated learning learns a global probability distribution by updating the global model based on the local models shared by different clients. Then there's a model aggregation, which allows the federated learning to train over the entire data distribution without disclosing the distributed training samples. So let's first go through the procedures of the federated learning. The federated learning process by iterating several steps. First is the parameter servers will initialize a global model and deliver it to all the clients in the system. Then secondly, each client will update the model using the local data, and send back its model updates, which is in the model parameters form. Then the server will aggregate all the local models updates, then send the updated global model again to all the clients. So this is a typical one round of training in the federated learning. We assume that each client data are from the specific source domain, has specific features, like in this sample, they have different backgrounds. The effective knowledge transfer among the clients in model aggregation is critical to the success of federated learning. So the goal here is to learn a global model generalizable to the target domain based on knowledge of these different client models. The challenge here is the source domain data first are not available during the federated learning, and the target domain data are usually unlabeled, which render the traditional method for domain transfer, like generation method, infeasible in the federated learning setting. To illustrate this point, consider multiple agents train separate models using samples with different styles due to their data collection environments. Then the goal here is to solve a novel task, leveraging the reusable information from this model's local task. Intuitively, it would be difficult to directly use the learned representations from the different tasks of agents due to all the noise and distractions in the background of the training data. We proposed a new multi-source domain adaptation method that disentangles the domain-relevant stationary fixtures from this different task and reuse the learned models of agents to improve the model performance in the new task. This framework consists of many three building blocks. First, the global fixture disentangler and the embedding matching, and finally, the federal voting components. I will go through these three different components in the following slides. So first, the global fixture disentangler learns to distinguish between the representations from a source domain of the clients and the target domain of the new task we want to solve. To learn an encoder that disentangle the domain-relevant fixtures from the source domain, we devise the global fixture disentangler by introducing a domain classifier in the server side that will take the learned representations from the client as the input and output the binary variable value for each input sample. And these binary variables will indicate whether the samples come from the client source domain side or from the target domain in the parameter server side. So when the fixture disentangler cannot distinguish whether an input representation is from the client domain of a client or it's from the cloud domain, the local encoder of the clients can output the representations that are close to the ones learned from the target domain. In particular, we encourage the feature extractor of the local model to distill features that are domain relevant by maximizing the use of the disentangler. If you consider the generative adversarial neural networks, we have a generator and a discriminator. So we want to train the generator to generate some samples that are indistinguishable for the classifier. So the principle here is similar to the generative adversarial neural networks to learn an encoder. And secondly, we further enhance the disentanglement of fixtures by measuring the high-dimensional distribution difference between the feature representations from the client and the target domain. To do that, we align the extracted representations based on the multi-kernel maximum discrepancy loss. This can encourage the learning of stable common features between the two domains. Here, we try to minimize the embedding discrepancy to achieve this goal. After we try to align the different representations from the client side and the cloud side, then what we want to do to update the local models of clients using the combinations of the different loops, which are the disentangler loops and the embedding loops and the empirical loops for the classification task. On the other hand, we also update the global model for the new task by using the aggregated parameters of the local models. So here we simply take the average of the model parameters from different clients as the new global models parameters for the next round training. And finally, we also propose the federated voting in this work. It's a strategy we use to further fine-tune the global model when there are no any label available in the new task. It tries to generate the pseudo labels for the novel task based on the plurality voting of the local models, which will allow the global model to learn better targeted task representations, improving the performance of knowledge alignment between different domains. Then we fine-tune the global model based on the samples from the target domain and the generated labels based on the voting of different local models. Okay, so for the experiments, we performed the evaluation in the two image classification datasets and text sentiment classification datasets for different transfer learning tasks. For example, the digit file is a collection of the 5-digit datasets, and the office character consists of the office object images in 4 different domains. And the Amazon review includes customer reviews from 4 different categories. We consider the different transfer learning tasks for each dataset. We use the one domain as a target task, and the remaining domains as the source task to train the model. For example, in the digit file, we can use sorry about that. So For example, in the digit file, we can use the empty set as a holdout target domain and the left for sets as a source domain to train a model. Then we want to evaluate the trained model's performance in the target empty domain based on the learned information from the different source domains. I show here the performance evaluation in the image classification datasets. In these labels, each column shows the performance of a specific transfer learning task. We performed an ablation study to evaluate the efficacy of each component of the proposed framework. The methods above the bars are the baseline methods we employed, try to compare with, and the methods below the bar are different variations of the proposed methods. We also consider the different voting scales influence on the final results by using different numbers of target samples to fine-tune the global models. I'll show in the plus voting small, plus voting large. I'll show in the tables, compared to the baseline method, we can achieve better transfer learning performance for the transfer learning task to tackle the domain shift problem. We also studied the effectiveness of the proposed method when applying the different model architectures. So basically, we find that if we can use a more complex encoder, we can better compare the different representations from the different domains. As a result, the performance improvements can be increased based on the complex model architecture we use. We further introduced this new metric called the group effect. A higher group effect score will reflect the more information loss in the knowledge transfer in the federated learning. By contrast, the negative score represents a performance gain instead from the transfer. And the graph illustrates the amount of information loss in the learning process. As you can see, when the learning was first initialized, the transfer loss was high because there was a little common information that could be reused at the beginning of the learning. As learning progressed, we started to observe some gain in the knowledge transfer indicated by the negative scores, and the gain at each round kept increasing until it converged at a certain time point. So compared to the baseline method, our framework allows the late convergence of the learning, which will contribute to a largely increased information gain during the learning. As a result, the model can obtain more reusable knowledge from the past task, and its generality to unseen domains has improved. Finally, I showed the TSNE visualization, which shows that our method can learn better knowledge transfer representations. So quickly to conclude, we tackle the problem of domain shift in the multi-party federated learning setting. We consider the domain generation under data confidentiality, and we studied the negative transfer in the model aggregation and devised the method to alleviate such negative transfer. And we found that our proposed method can introduce this late convergence of knowledge transfer to improve the generality of the global model to tackle new tasks. Yeah, that's all. Thank you so much for listening. I'd like to answer your questions.
We have time for 2 questions.